everybody. Welcome to another lesson of math from chapter 10. Today we're going to look at 10.3. I would encourage you to read through the notes that I sent on Canvas, and there's certain parts of those notes where I said watch video for further explanation. So I've written down probably 10 or so examples to just kind of work through here so that you can watch me, you can hear my explanation, and hopefully that will help your understanding of this particular lesson. So remember that if we have a perfect square underneath our square root, we already know what the answer to that is. So don't lose sight of the fact of some of the things you already know. The square root of 16 is 4. The square root of 25 is 5. And so on and so forth. So today's lesson is about what to do when we don't have a perfect square underneath the radical. So our first example looks like this. The square root of 27. And the idea here is there a perfect square within the number 27? Can I break that down into the product of two numbers, one in which it would be a perfect square? So 27 can be rewritten as the square root of 9 multiplied by the square root of 3. And because 9 is a perfect square, radical 9 just becomes 3, and that 3 comes straight down. And so the square root of 27 reduces to 3 radical 3. Now, that's all good and fine if you can recognize these perfect squares within this number. So what happens when you can't? Well, let's look at this same example. We already know what the answer is. Let's look at this same example again and use a different method. And I'm not sure if you would see this method anywhere else but kind of right here, because this is how I've always kind of explained it to my kids. So, step 1, we're going to break this down into a product of primes. You can start this however you want. So 27 really only has one way to break down. 9 times 3, and then 3 times 3. Because it's a square root, there's a little tiny 2 right there that we don't tend to write down. It's implied. So we are going to circle any numbers that have a pair of 2. So it doesn't matter. We have 3 3s here. It doesn't matter in the slightest which 2 3s I circle. So I'm just going to pick those 2. One of the things that you circle is going to cancel. Any number that is circled is going to break outside of that radical. So that 3 right there is going to break out. This 3 right here is going to stay inside the radical. And so this is just a different example to show you that the square root of 27 is 3 radical 3. Let's do it again. We're going to add variables. We're going to add higher powers. But let's do something similar to this one again so that you kind of get a handle on it. Let's do the square root of 72. Someone could see 72 and break that down as 8 times 9. Somebody else might see 36 times 2. It doesn't matter how you break it down. We all end up with the same prime numbers down at the bottom. So 72 is 8 times 9. 8 is 4 times 2. 4 is 2 times 2. And 9 is 3 times 3. So we're going to look for our pairs. We have a pair of 2s, one guy cancels. We have a pair of 3s, one guy cancels. And I have that 2 right there that's at the bottom of its tree that didn't get circled. This guy right here is going to stay inside the radical. Anything that's circled comes out. So that 2 breaks out, that 3 breaks out. And so because I have 2 numbers that are breaking outside of the radical, I'm going to multiply those. 2 times 3 is 6. That 2 stays underneath. So our final answer is 6 radical 2. Not everything can be broken down. So let me double check my example list here. The next one is the square root of 30. So you have to check to make sure nothing can be broken down. There's not any pairs, things like that. So this is 3 and 10. Somebody else could have written it as 5 times 6. 10 is 2 and 5. We don't have any pairs at all. So when there's no pairs at all, it just stays radical 30. That is its most simplified form. So we're done. There's nothing we can do. All right, let's throw in some variables. Oh no, scratch that. What happens if we're multiplying? Because also in this section, I believe, is multiplying radicals. So we're looking at this. You might start immediately breaking those down. I would highly recommend multiplying them first so that you just have one radical to deal with before you start finding your pairs. So 10 times 15 is 150. And now you already know what goes into 150 because you just did it, 10 times 15. And then you can break it down from there. So 10 is 2 and 5, 15 is 3 and 5. Now, I put the 5 way over here on purpose because sometimes your circle might look a little weird, but that's still a pair of 5s. One guy cancels, the thing that's circled breaks out of the radical. In this case, there are 2 numbers not circled. We're going to remultiply those together. So the square root of 150 becomes 5 radical 6. Let's add in some variables and see what we do if there's a variable in our problem. So let's do the square root of 175 x squared. All right, 175, it ends in a 5. So you know it's divisible by 5. It's going to be 5 times 35. 35 can be broken down to 5 times 7. We have a pair of 5s. One guy cancels. So that 5 breaks out. That 7's underneath. So that 5 breaks out. Even on my chalkboard, I run out of space. That 7 is underneath. Now we have to deal with the x squared piece. There's a couple different ways you can look at this. Because it's just x squared, you can break it down. You have x times x, circle your pairs. Excuse me, one guy cancels. And so that x breaks right out of the radical. Another option is, there's a little 2 right there. Remember that that is the denominator of the fraction. So this really can be rewritten as x2 over 2, or x to the first power. So it reduces itself if you use the properties from 10.2. Excuse me. Also, let's look at another one where we have a remainder, and I'll explain another way you can look at those variables. This one's going to be my personal favorite. Let's do the square root of 5 x to the third. And I'm going to do a multiply, square root of 15 x to the 8th. So multiply first. 5 times 15 is 75. Remember, we're going to add those exponents. So we're going to have x to the 11th. 75, you can write down 25 times 3. I already know it's 5 times 15. 15 breaks down to 5 and 3. Circle your pairs. One guy cancels. That 5 comes out. That 3 stays underneath. So 5 is out. The 3 is under. All right. Now I have this x to the 11th. I don't really want to write out x 11 times and circle all of those pairs. Remember that this is a 2. All right, if I rewrite this as a fractional exponent, I get x to the 11 halves, which isn't really helping me simplify there anyways. So, or either, I should say. So what I suggest you do is I would divide 2 into 11. 2 goes into 11 5 times, meaning there are 5 pairs of x's. So we're going to have x to the 5th on the outside. There's one remainder, and so we have x to the 1st on the inside. So this is my final answer here. Let's do it again, and this time I'll have multiple variables in my problem. Let's do the square root of a b to the 5th, c to the 8th. All right, so I didn't even deal with coefficients. I showed you several examples of that. We'll circle back to that with some higher powers as well. So there's a little 2 right there. A to the 1st, nothing can break out. There are no pairs if I just have a single A. So my final answer will have A to the 1st. B to the 5th. Let's take 2 and divide it into 5. 2 goes into 5 twice. 2 times 2 is 4, and we know we're going to have 1 remainder. So I have 2 pairs of A's outside, A squared, and I have, sorry, that's a B. I'm not going to go back and fix that. I've already been through this. You would not even know what take we're on right now. I think I've been at this for quite some time. All right, so that's B to the 1st. 2 goes into 5 twice. There's 1 remainder, B squared on the outside, B to the 1st on the inside. Let's take that C to the 8th. 2 goes into 8 4 times. 4 times 2 is 8. You know there's not going to be a remainder because it's an even number. And so we're going to have C to the 4th power. That guy right there are these exponents right here. If I write it out for you, just to give you that visual once, let me erase. Remember that was C to the 4th. If I write out C 8 times, there's a pair, 1 guy cancels. 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 1, 2, 3, 4. C to the 4th was on the outside of that radical. All right. I think now I have to put on my glasses again. I think we're headed into some higher roots at this point. Yes. So let's look at the cube root of 16. Step 1 is going to be exactly the same if this is any number other than just a regular square root. All right. So break it down into a product of primes. So 2 times 8. 2 times 4, 2 times 2. But we're looking for perfect cubes now, not perfect squares. So perfect cubes is a number multiplied by itself 3 times. So we need to circle 3 of the same number. I have 3 2's right here. When we circle, instead of just 1 guy canceling, 2 members are going to cancel. So cancel. Cancel. That 2 breaks out. This 2 stays inside the radical. So this reduces to 2, or simplifies to 2, the cube root of 2. And that's our final answer. Something similar is going to happen when we have exponents. Instead of multiplying by 2, we're going to multiply by, or not multiply, instead of divide by 2, we're going to divide by 3. So what if I have something, I'm going off script here, just to show you what these variables look like. And so if I have x to the 5th, and I choose to write it out, I have x, 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 x. I have a perfect group of 3. 2 of them cancel. I have 2 remaining that don't really make an entire group because I have 1 group that was x to the 3rd. 1x is going to break out. And these 2 x's get remultiplied and they stay underneath the radical. When it comes to y to the 9th, I might not choose to write out y 9 times. But remember the rule, we can always take that number and divide it into the exponent. So how many perfect groups of 3 are there in 9? There are 3 groups with 0 remainder. So y to the 3rd goes on the outside. And that is the final answer there. All right, what else do I have for you? We did something similar to that one. You can continue this pattern. I'll show you this one. The 4th root of 32, x to the 9th. So the pattern kind of just continues. Step 1, break it down. 2 times 16, 2 and 8, 2 and 4, 2 and 2. We need groups of 4, and 3 of them will cancel. So everything always gets crossed off except for a singular number. So I need to circle all 4 of these 2's, and 3 of them cross out because only one of them is going to break out of that radical. So that guy's out, and that guy's in. So it becomes 2, 4th root of 2. I can write out x 9 times and circle my groups, or I can say, gosh, how many perfect groups of 4 are there in 9? There are 2 groups with a remainder of 1, so I have x squared on the outside and x on the inside. The only way we could make this a little bit trickier, well, maybe it's tricky enough for you as it is. Sometimes you might see a sample problem. I don't know how many on the homework I assigned. I don't feel like I assigned that many. But what happens? Oh, this is going to show us a couple of things. All right, what happens if there's a number outside of the radical? So I think there's some sample problems like this in the handwritten notes, and there's some that are different in the book as well. So 5 times 2 is 10. You just multiply those together. So outside to outside, inside to inside. So those guys are multiplied together like that. So there's our step 1. Now, here's the thing. You get so into doing the breakdown method that you don't just stop, not you specifically, but students in the past, this is the trend, that you don't just stop and kind of look at your number. 36 is a perfect square. We know that to be 6 times 6. So if you go to break it down, you're going to end up with a pair of 2's and a pair of 3's, and you're going to just go through the motions. That breaks out, that breaks out. There's nothing left underneath the radical because it is a perfect square. So when you break out that 6 times 10, everything is multiplied. 6 times 10 is 60. X squared and the square root of x squared is just x to the first, or just x. Let me double check my notes. Bear with me here. I have 1 on here remaining where we have it to the 5th root. So let's do that one. And this is the main skill in section 10.3. So we have the 5th root of a to the 6th, a to the 10th, and c to the 13th. We're going to divide, see what's remaining. I hope you're kind of picking up the pattern of all of this. We need groups of 5. So 5 goes into 6 once with a remainder of 1. So I'm going to have a to the first on the outside. Don't forget to rewrite that little index. And I have a to the first on the inside. 5 divides into 10 twice with no remainder, so there aren't going to be any b's here. It's just going to be b squared. And 5 goes into 13 twice with a remainder of 3. So we have c squared, and then we have c to the 3rd. That looks like a really complicated answer if you're just kind of staring at it, but when you break it down and see where each piece comes from, hopefully it makes sense. So again, email me, text me with your questions. Good luck on 10.3, and you guys stay safe. Thanks. Have a good day.